Your Moodle site can be healthy tonight and unrecoverable tomorrow. A failed upgrade can damage the database. A lost VPS can take the server and every local backup with it. And if you save only the database, Moodle might return with missing files. Save only Moodle data and the courses, users, and settings are missing. Today, we will build a complete nightly backup, move one copy of the server, and restore every component into isolated test targets. Because a backup is only useful when you have evidence that it can be restored. Welcome back to Open Education Operations. Let's get to work. Before we begin, a quick note. This walkthrough takes you through the process step by step, but it uses privileged commands and performs a restore test beside a live Moodle installation. You should be comfortable checking Linux paths, permissions, and database names before applying these commands to your own environment. Whenever possible, rehearse first on a test server and keep a current recovery point. The companion guide includes the complete commands, additional verification, and safety precautions that are not practical to cover in the video. With that said, let's begin with the three connected parts of a complete Moodle recovery point. The database contains users, courses, settings, and activity records. Moodle data contains the files those records refer to. And the Moodle code tree contains Moodle itself, plus installed plugins, themes, dependencies, local changes, and config.php. Course level.mbz files solve a different problem. They can recover or move selected courses, but they are not a complete site backup. Before creating full backups, we will measure the two file trees, confirm the database engine, and check the free space on the server using these commands. On this server, the code tree is about 1.7 gigabytes, Moodle data is 78 megabytes, all 490 Moodle tables use InnoDB, and the root file system has 91 gigabytes available. Your values will be sure different. The important point is to leave room for the temporary working data as well as the completed compressed backups. That InnoDB result matters because the backup script in the next step can use a transactional snapshot to create a consistent database dump without taking the site offline. Now that we know what must be protected and how much space it needs, we can create a destination that ordinary accounts cannot read. The backup will contain personal data, password hashes, uploaded files, and a copy of config.php. So it needs the same protection as the live site. We will create a root-owned directory with mod 700 and confirm the saved permissions using these two commands. This line here means only root can enter or read this directory. We will keep that boundary intact even when we later move one selected recovery point off the server. With private storage ready, the next part is the job that builds one complete recovery point safely. This is the largest script in this video. Rather than pass a long file without context, we will first open the local working copy in my editor, I prefer VS Code, and review how it is organized. These give us a readable view of 5 logical blocks. The first block controls safety. Strict shell mode stops on command, variable, and pipeline failures. The private umask protects every new file. Flock refuses an overlapping run. And make temp creates a hidden partial directory. If a later command fails, the trap removes that incomplete work instead of presenting it as a usable backup. The second block uses --single transaction to capture a consistent view of the InnoDB database without taking this site offline. It streams the dump directly into gzip. --quick keeps memory use predictable. As for --hex-blob, it represents binary values safely, and routines, events, and triggers are included. Because the script runs as root, MariaDB's local socket authentication avoids placing a database password in the script or process list. Moodle data is archived afterward from the live file system. That makes this a practical small server baseline, not a perfectly simultaneous database and file system snapshot. A busy or clustered site should use a maintenance window or coordinated storage snapshots. The third block archives Moodle data and the Moodle code. Cache, local cache, temporary data, trash, and sessions are excluded because Moodle can regenerate them. The runnable code tree remains complete, including plugins, themes, dependencies, local changes, and config.php, while the large.git history is omitted. The fourth block records configuration, git identity, and one SHA-256 manifest for every artifact. These hashes detect corruption during storage or transfer. They are not encryption, and they are not a signature against an attacker who can replace both a file and the manifest. The final block publishes the recovery point with one rename only after every artifact exists. Retention can delete only completed timestamp directories directly beneath the fixed backup route and older than 7 days. Those path and age restrictions matters because retention is the part of the script that removes data. With that structure clear, we will return to the SSH session and install the same script on the VPS in one pass. Next, we will make the script root only and perform one syntax check before executing it. Backup script syntax OK means Bash can parse the complete file. It does not run the backup, but it catches typing and structure errors before the script is scheduled to run unattended. The script is installed. Now we will run it manually once, where we can watch every stage and inspect the completed result. A manual first run is always important, and in this case, it separates backup script problems from scheduling problems. We will time the complete job and keep the final timestamp and size visible. The output moves through database, Moodle data, code, configuration, and checksums in order. On this server, the completed recovery point is about 106 megabytes, and it finishes in roughly 20 seconds. Larger sites will take longer, of course. Now we will select the newest completed timestamp and verify a checksum manifest from a root shell. Each OK means the current file matches the SHA-256 value recorded when the recovery point was published. On this server, that's 8 files show that none of the protected artifacts changed or become corrupted after creation. Checksums provide integrity evidence. Later, the restore test will show that the database and archives can actually be read back. One successful command is useful, but a backup system must also run when nobody is connected. Let's put the same backup script behind systemd. We will use a one-shot service for the job and a timer for the schedule. First, the service file. This service waits for MariaDB, checks that both live file paths exist, runs the same backup script once, lowers its CPU and disk priority, and removes the normal start timeout so a large backup is allowed to finish. Next, let's do the timer. On calendar follows the server's local time zone. This server is configured for UTC, so the base time is 3:15 UTC. The timer adds up to 10 minutes of randomized delay and catches up after downtime, which is why the displayed deadline can fall anywhere between 3:15 and 3:25 UTC. Before enabling either unit, we will set their standard permissions, reload systemd, validate the file, and ask systemd to interpret the calendar using these commands. Systemd-analyze-verify checks how systemd reads both unit files, while the calendar command shows the next time represented by the schedule. A clean result tells us that the automation has been interpreted as intended before it is enabled. Persistent equal true may immediately run one catch-up backup if today's scheduled time has already passed. To avoid launching an unnecessary duplicate, we will count completed timestamp before and after enabling the timer. Then, we will start the service manually when no catch-up run appeared. The manual run showed that the script can create a backup. This run shows that systemd can launch the same job successfully, while the timestamp comparison prevents an immediate catch-up run from being duplicated. Now we will inspect the service result and the timer's next run. For a completed one-shot service, inactive and dead are normal. Result equals success and execution main status equals 0 prove that the job finished, while the timer stays active with a future run. This creates the schedule without alerting anyone when a backup fails. Monitoring and notifications belong in a future video. Automation protects us from forgetting to run the backup. However, backups stored on the same server can disappear with it, so the next recovery copy must be stored off server. The canonical directory remains root only. Instead of weakening it or enabling root SSH, we will create one short-lived administrator-owned stage for the exact timestamp we want to transfer. First, we will create that private stage, copy the selected timestamp into it, change only the stage copy's owner, and verify the manifest again before transfer. We will do this using this command. The stage is readable only by the administrator and contains one completed timestamp. When all 8 hashes return OK, the staged files match the root-only canonical backup before they leave the server. The stage is only a transfer bridge. It is still on the same server and disk, so it is not an independent backup. I will move now to my Windows workstation. We will first open the transfer helper and briefly review what it will do. The helper is organized in 4 blocks. First, it validates the timestamp, SSH alias, destination, and available space. Then transfers the exact stage directory and checks the CSP exit code. After this, it rejects unsafe manifest paths and recalculates every SHA-256 hash. And then it prints one compact summary. With those safeguards confirmed, we will run the helper using the timestamp printed by the server. I will copy it from the output of the previous command in my SSH session. The // prefix runs the script from the current PowerShell directory, while -backup name selects the exact stage timestamp. On this server, the 106 MB set transferred in about 29 seconds and all 8 files matched. Transfer time will vary with the connection and backup size, of course. After all off-service checksums OK and transfer and verify complete appear, the Windows copy has been transferred and verified. The administrator readable stage on the VPS was created only for this transfer, so it is no longer needed. This cleanup validates the exact timestamp and confirms that the root-only canonical backup still exists before removing only that temporary stage. Great! Only the temporary readable copy is removed. The private canonical backup remains, and the independently verified Windows copy contains the same 8 protected files. For a stronger production design, store the second copy in a separate provider account or region with encryption, versioning, and immutable retention. A workstation copy is useful, but it should not be the only offsite destination. We now have integrity evidence in 2 places. The important question is whether the backup components can be read back successfully. Up to this point, the checksum results have shown that the backup files still match the bytes recorded in their manifest. That is important integrity evidence. but it does not tell us whether MariaDB can import the SQL or whether the archives can be extracted in the structures Moodle needs. Of course, everybody loves backups. What they actually want is restores. That is why we will now perform a component restore test. We will not override the live database or extract anything over the live Moodle directories. Instead, we will use scratch targets, which are temporary test locations created for this drill and removed afterward. They remain on the same VPS, but fixed database names and file paths keep them separate from production. The live database is Moodle. The test database is Moodle_restore test. The live files remain under /var, while extracted test files go under /temp/OpenEducation operations restore test. If the SQL imports successfully, the privacy-safe database signal match, and both archives extract with their expected structures, we have evidence that the backup component can be read back. This is still not a complete clean server disaster recovery test, and we will define that boundary clearer later. Before creating the scratch targets, we will confirm that the live database exists, both test locations are unused, and the backup service is not running. The Moodle result confirms that the live database is present. No result for Moodle_restore test together with the two absence and inactive markers establishes an unused scratch area and a quiet backup service before the restore begins beside production. Now we will create only Moodle_restore test and load the compressed SQL into it using these commands. The fixed target after MariaDB is the scratch database, never Moodle. Pipe fail makes either decompression or import failure visible. On this site, the import completed in about 4 seconds. Now the important part, the comparison. The live schema against the restored one, plus 2 privacy-safe content signals. No usernames, email addresses, or configuration values will be displayed here. Both databases contain 490 tables. The user row totals match internally, and both contain Moodle's core version row. This is stronger evidence than counting statements in the compressed file because MariaDB has actually loaded and queried restored data. With the database restore checks passed, we will create one private scratch directory and extract Moodle data and code beside each other. Both archives are extracted only under /temp/OpenEduOps restore test. -- no same owner prevents the archive from applying stored ownership inside this test location. Finally, we will verify the two structures and record their expanded sizes without listing uploaded files or opening configuration contents. The Moodle data contains file directory, and the code archive contains Moodle's 5.2 public/version.php plus config.php. On this server, they expand to about 62 megabytes and 658 megabytes. The code is much smaller than the original 1.7 gigabyte tree because the 988 giga history was intentionally excluded. Moodle data is smaller because cache, temporary data, trash, and sessions were left out. At this point, we have shown that the checksums pass, the SQL loads and matches, Moodle data extracts, and the runnable code tree extracts. This is a component-level restore test. We have not pointed Apache at this copy, logged in to a restored site, or rebuilt a clean server. Those are application and disaster recovery tests, and they belong on an isolated temporary host, not beside production. The test has produced the evidence we need. Now we will remove only the scratch targets and prove that production remains intact. Before either deletion, we will display the live and scratch names together. Only Moodle_restore tests and /temp/OpenEduOps restore tests are disposable. The live database, live files, and canonical backup are preserved. We will now remove those 2 fixed scratch targets. The command contains the complete scratch database and directory names. It does not use a wildcard and does not reference either live file path. Next, we will confirm that the Scratch targets are absent and the live components remain present. The Scratch database query returns nothing. The Scratch directory is gone, and every production component remains available. For the final check, we will confirm that the timer still has a future run and follow Moodle's public redirect to the page a visitor reaches using these two commands. The timer remains active. The live Moodle site reached its login page with HTTP 200, and the component restored rel has left production unchanged. This gives us a tested backup baseline. A complete server loss recovery still requires an ordered rebuild on a clean, isolated host. The evidence in this video supports a specific claim. This recovery point is complete at the component level, and its protected data can be read back successfully. We verified the local and off-server copies, imported the SQL into an isolated database, compared meaningful database signals, and extracted both file archives into Scratch storage. We also confirmed that the live site and its backup schedule remained healthy after the test. This does not demonstrate a restored Moodle site serving traffic from a clean replacement server. Infrastructure reconstruction, application startup, and operational validation are part of a broader disaster recovery exercise beyond this recording. For production, pair this component test with a periodic clean host recovery exercise in an isolated environment. A successful end-to-end exercise is the evidence needed before claiming complete server loss recovery. With the recovery boundary clear, let's close with what this server can now do automatically and what evidence supports it. This Moodle server now creates root-only, time-stamped backups of the database, Moodle data, complete runnable code, configuration, and code identity. It publishes only completed recovery points, prevents overlapping runs, keeps 7 days locally, schedules the job through systemd, and moves a checksum verified copy of the server. More importantly, we loaded the SQL into an isolated database, matched its structure and privacy-safe content signals, extracted both files archives, and proved that the live site still works afterward. This site can still fall tonight, but now it can come back tomorrow. So protect all 3 Moodle components, keep a copy outside the server, and test the restores before you need it. If that's the kind of Moodle stack you are building, subscribe to Open Education Operations. There is more of it coming. I will see you in the next one.